channel. And today we will be seeing how to scale a SQL DB. And in this video, we will also see how a SQL DB saves data and how it processes data so that we can optimize our database and use to its full strength for high scalable systems for where data is so much we need high throughputs, high write throughputs. So yeah, let's get started. Please watch this video till the end. You will get many insights which are not available in YouTube, and you will get that in this video. So let's get started. Uh, when we are designing a system, when it is a small system where they are very limited number of data, like on less than 100 MB of data, so yeah, we can simply create one Postgres database and we can perform read and write. This will work completely fine. But what happens if the write throughput keep on increasing and also your read throughputs are increasing, your use cases are changing, your number of people on a systems are increasing, you are increasing number of servers. So how will you optimize this? Because there can be use cases where you are running very complex queries, uh, and it is taking a lot of time also, and plus you want to write data on also that table which is taking a lock, and that lock is delaying your query again. So how can you do that? So for now, what we can simply do is we'll see how to optimize reads first. Then we'll see how to optimize writes. Okay, so let's suppose we have a two table where I have one user table and one transaction table. So ID is the primary key of this user table, and user ID is foreign key of this transaction table. Okay, which is pointing to this ID of table user. So if we see, this example, we'll see to how to optimize reads here. Okay, so let's see. First of all, to optimize read, what we can do is we can separate our database nodes. Like we can create two nodes. One is master, another is slave. So the all the write requests coming to our database will go to this master DB, and we can have this asynchronous syncing which is running in the background so that data in the slaves are updated which is in master, and our server will always make connections with our slave database only so that it can read and it is not affecting this master. Okay, so this is very helpful, but there's a con that DB all have some stale data which is not updated. It may take some milliseconds to get updated data. So if you're working on critical data, which you if you want to query critical data and you know this query is straightforward, then you can simply run it on master DB also. Otherwise, I'll say that we should run all the read queries in slave. Let's suppose you have an application and you have a backend side, or you can say admin portal of that application also, but you don't want that your application admin portal should affect your current ongoing application. So what for that, what can we do? We can simply create um, one slave here, one more slave, and again this asynchronous writes will happen in this slave also, and we can say that this slave will only connect for admin purpose. Okay, so when we are running queries from admin server, we will always connect to this slave db, this slave db only. So like this, if your use case is running complex query for analytics or other purposes, you can create another slave for that analytics purpose. So like this, you can create different readers based on your requirements. Okay, and for writes, we'll write on master, and all the updates will be synced to our slaves. So this is one way where we can do optimize reads. But let's suppose your table is continuously growing and you want to query on multiple columns. Like for transaction, I want to query on user ID maybe, or created on when it was because I want all the transaction between certain period of time, or I want all transaction for an user, and that user have millions of records. So what we can do here to fetch the record in low latency. So what we can do is we can create index. Yeah. So what index is? Index is like in this table, if we want to fetch data for a user, so we can create index on this user ID. So what this will do, if we apply a filter where we are adding this user ID filter, like queries where user ID is 1. So uh, thi- this index will come into play, and all the records are fetched using that index. Okay, so for example, we can see that if there are 3 rows of this user ID, and we have made an index here, so we in database what it will do is it will keep that user ID like 1, and against that it will keep that block where where this user ID's records are present, that block, so that our query will go into the disk and add that particular block only and fetch data from there. For your information, I will let you know that we save data in file format in disk in SQL DBs. If we say, for example, we are using Postgres here. So in Postgres, what we do is we save data in files in our disk. So if we want to go to a particular block of the disk, this user ID, we can map this with user ID and that block ID like this, and we can directly go to the block and fetch that data instead of checking all the records and seeing where user ID is one. That will take a lot of time, but this index can save us. So we can create index on user ID. Now you'll say, so if index is so fast, why not we create index on amount also, type, created on everything? Because see, ID is always indexed by default. So why not create an index for every column? So that is a very bad approach. First of all, it creating index takes some space, storage space. Second, when you will create an insert now, it has to re-index everything. Why re-index? Let's give me example of one index. One index data structure is B-tree. Let's see how B-tree looks like. So let's suppose this root node. We have to go to maybe user ID 7. So 500. So see, it is just like a binary tree. So 7 is less than 500. So we go on the left side. Now see, 20 is there, 150 is there. 7 is again less than 20. We'll go on the left side. Now we'll see that 7 is greater than 5. So we'll go on the this node. Okay, so somewhere here our 7 will lie. Uh, like this, for example, if we have like maybe 70, let's suppose. So for again, we'll go on the left. 70 comes after 20, so it is here in middle of 20 and 150. Again, 70 comes after 25 and between 100, so it will again here be middle, and there will be one child. We will get that child root, child in child ID, and against this child ID, we'll be having this block ID. So from there we can see. So if we create index on every column, every time when a new user ID entry comes here, it has to do re-indexing. It will take some time. So your insert will insert will started taking time, more time to insert a data, which will again increase the latency, and that we don't want. So we should avoid all the indexes which we don't want to optimize our writes. Okay, this is one thing. Second thing is, database uses a table called PG statistics internally to see where we want to how we want to query a data. Like if you've given a filter of user ID, this table first database will see, and it will have the it has already analyzed all the ways you can query. So if you see that for querying only on user ID, it will know, yeah, I have an index Let's use that index to query that data. Okay, so it has all the plans ready beforehand, so that we can query data. Now, what if I say I am writing a query where I'm saying like user ID is this and type is equal to credit. Will my index be helpful here? It will be, but not to its full in strength, because we have created index only on user ID. For this, so it will fetch user ID, all the transaction for the user ID, but it will again do sequential scan on credit and debit. So what we can do here, if we want to know, we know our query patterns where we'll be using query where we have two filters or three filters. We can create a composite index of that. Like ID and type can be one composite key, and we can create index on this composite key. So we have to be very sure about how our query patterns will look like. Based on that, we can create our indexes. Okay, so this is one way where we can optimize. One more ways, like see, this is a very big table. Okay, so this is a sequential increasing data. It will keep on increasing, and when we get these type of tables where these are the child tables, no, its primary key is nowhere the foreign key, and it is a sequential data. So what usually people do here is we can create partitions of this, different partitions based on created on month. Maybe we can apply, we can say it at partition key. Okay, so like for every month of data we will be saving one table. Like for August there is one table, for September there is another transaction table, for October there is another transaction table for that year. So for month and year we can create a transaction table. And if we want to query of user data, so in a feature, if we want to show all the transactions for a particular user, we can show them month wise. Like you see in your bank, you if you go and fetch all your transaction, it always says you to apply a filter range so that it can optimize its query. So where we can always have this created on with us, so that it can search in that particular partition only, and in comparison to the complete table, partition will have less table, so it will also do query faster. Okay, and if you want to delete data which is more than 1 year ago, we can just simply delete that partition. Like January 25 has come, so we can delete partition of January 24. Okay, so like that we can delete one partition at a time, and deletion is a heavy operation in database because again it do the indexing. So if you want to delete a, if you want to perform a bulk deletion, it is very expensive. It will take logs. It will take lot of time. So instead of, we can create partition table and drop that table or truncate that table at for once. Okay, so this will be very helpful, and it is used widely in all the product which you can see, which you use in your daily life. This partition is a very common technique to optimize our DBs. Okay, now coming forward, I think all the read optimizations are clear now. We have done partitioning, we have created index, we have created read replicas. I think that's more than enough to optimize a SQL DB when we talk about our reads. Okay. Uh, Now come to optimizing writes. Writes optimization is very important. How database writes. So this, what we see here is, from a server we hit a request of write, and in that DB the record is written. Okay, but no, what, let's see what actually happens when we do writes inside our DB. So this is something which happens internally when we are doing writes. Okay. So as soon as we do a write operation, it writes in the memory or in the shared memory. It doesn't write on the disk. So how we can say that it is following ACID property? Because in ACID property, there is one. uh, for D it stands for durability. Like if we have written a data, it will always be there. Okay, so how this is our data is durable. So for that, what we can do is simply uh, when what database does is simply is it write in the shared, but it writes that operation in a write ahead lock memory file. So in memory file, it is writes in that log file, and as soon as you commit a transaction, like you say, yeah, I have done my transaction, commit it, it flushes this all the records from this file to its in the disk. This file is being flushed to this disk, written in disk, and from this disk we write into a table, into the disk table. So in Postgres, the data is written inside files, and that files are saved in the disk. Okay, so this val file, our database will read all the operations and write in that disk. You'll get to know more how this when you get to know that how this log files are written. So this is written something like this. Okay, so it is an incremental operation. uh, every write are first incremented in this log file first. So we increment this, like we have an offset, transaction ID, what operations we are doing. Okay, we have written every data here, and let's suppose there are 10 records like this. And as soon as this we flush in our disk, this table will pick it, read one operation, update it in the disk, in the file storage where data is, and then update the index, and then we'll mark this offset as we commit this offset, like this operation is done. So database sees that in uh, log file val files till what offset we have persisted our data, so saved our data. Okay, so it keep track of this offset. So if there's some issue like server goes down, there's network outage or anything happens, bad happens. So whenever it will come up na, it will see till where which offset I have already written, and from next offset it will again start writing, so that it get the updated data in the database. So this is some how things are written, and it is done in sequential order. So this is the benefit of val is like, if there's any issue, we can simply read back from val file and update the database again if data is lost. Okay, and it also takes some time to do operations on index and all, so it failure can happen any time. So this val file, if we have record in this val file, we can again see this val file, okay, what right user wanted to do, and that can be done in the disk. So these are the benefits here. And yes, obviously shared memory uh, will be here for some time, then it will be flushed and all the records. So till then, till when this we are not writing in disk, if there is a select query comes, so we can return result from the shared memory only. So it works as a cache. If data is in the shared memory, return it. Otherwise, go and search in the disk. Okay, so it will never search the val file. It will always search first the cache and then the disk. Okay, so if there is any issue taking time to write in disk, till then we can serve a traffic from shared memory. So that is why shared memory and val is very important. This is how it is written in our database. Now comes to the part of um, how how this one row in DB is saved. How one row is saved. So if we do a select operation, like see, I've run this query. There's also one payment table in my machine in Postgres. So I've run. So this CTID min max is not the column which I created in my DB. Okay. So this is by default created by Postgres in every table. So if I select, if you do select Sarna, this will never come up. This you will not get this. So I have to type CT ID min, x min, x max, payment ID amount from payment where ID is this. So this is the ID. Now, if I do an update, if I run this update, then what will happen? For same payment ID, so what will happen here is, so this is a primary key, okay, payment ID. So what you will say that CTID, X min, X max, payment ID will remain same, only amount will become 1000. No. So in a Postgres, what update do is it doesn't update, it rewrites that row. Let's see how. We'll do that. The CT ID you can see is 03, now it becomes 08. The X min is 1689, it was earlier 1598. Okay, so these two values are changed. What it means? It means like every row is always inserted, and this CTID will tell that where this row is, exact location of that row in a disk is what this CTID will tell. And Xmin, Xmax are used to maintain versioning of what is the latest version. Let's suppose you are doing a lock on this row. Okay, so what DB will do is it will create a dummy tuple of this row, and it will create a different version dummy tuple, and when a read query will come now, that will be read DB will read give response from that for that read query from that dummy tuple. Okay, it will not affect the original tuple because we have a lock on that. So we'll allow user to do write as well as read at same time. It will help. It will help our deadlock. It will help to not have any deadlock in our system, because read and write both can happen at same time because of this versioning. But what happens to the version as soon as logged is released and we have done the update? As soon as the write is done, the lock is released and the old tuple is marked as deleted. That is why when I ran this update command, it only returned one row, because that was marked as deleted internally inside Postgres, and it will never return that row. Okay, so now we have the location of this tuple is some different, so that is why CTID is different. It is different version. So Xmin is also different. So yeah, so what happens now? You'll say that deleted tuples are inside our files. It must be taking memory, storage, because if we are working on a system where there's high write throughput, so every time these tuples will be created and it will be marked deleted and it will remain in a database. Okay, so for that, what we can do is there are commands like vacuum, vacuum full, and we can run this both vacuum and vacuum full with analyze. So let's see what this do. First of all, when we run vacuum, vacuum full with analyze, so this analyze will do is to do again plan our query and save the planning inside PG statistics, so that read query are optimized, are up to date. Okay, it will forcefully save Postgres to go and again do planning. But what this vacuum will do? This vacuum will simply delete all the deleted tuples then and there. Also, when there's high right now reindexing happens, there may be chances that a new index is created. Okay, so old index values or old index tuples are also there. That is also marked as deleted. So this vacuum will simply delete every deleted one. But it will not give memory back to our operating system. It will only release that memory for that table inside that file. But what vacuum full will do? Vacuum full will simply apply a lock and full table, see what are all the non-deleted tuples, and it will write that file, that all the record into a new file, and all the rest of the memory is written back to operating system. Okay, so vacuum full will always have a lock and vacuum will not. but it is recommended to run these vacuum commands with analyze so that new query planning is done. Plus, it should only be ran at time when there is where traffic is very low, because it do impact our system performance. So always run vacuum commands only when the traffic is very low. Okay, so I think we have covered most of the thing: how database internally saves data, how we can optimize it, how say this vacuum thing we can run it every day, maybe for high write throughput systems at night when traffic is very low. So like this, our data size will also reduce, our write will be optimized. So we have seen how writes and reads are optimized, how SQL database data is stored inside it, how it handles failure conditions. Okay, so yeah, we have, I think, covered all the topics. Uh, do let me know if you want to get to know about any other thing. I'll be creating videos soon of why should we choose SQL DB, and why should we choose no SQL DB, and when to choose, and all, and also how internally NoSQL DB works. So I'll create a video. If you want to see a video on a specific topic, do let me in the comment section and let me know how you like this video or not in the comments. Yeah, till then, take care.